Okay, let's get right into it. Welcome to this explainer, where we're going to completely demystify the mechanics of moving bodies that actually lose or gain mass while they're in motion. We're going to challenge some fundamental assumptions you probably have about how things move, taking a journey from the really counterintuitive behavior of falling chains all the way up to the monumental high-stakes physics of spaceflight.
So here's our roadmap for today. First, we'll cover the physics of changing mass. Then we'll explore the flat car analogy, unlock the famous rocket equation, figure out measuring engine efficiency, confront what's known as the tyranny of the rocket, and wrap up with a multi-stage solution. It's a fascinating progression that is honestly going to change how you view momentum.
To truly wrap our heads around rockets, we've got to start with the foundational rules. Section 1, Physics of Changing Mass, Physics in Motion.
Let me throw a quick question at you. Does a falling object always accelerate at exactly g, the standard acceleration of gravity? Now, you've probably been taught that gravity acts uniformly on all falling objects, whether it's a bowling ball or a feather in a vacuum. But what actually happens when an object's mass actively changes during its motion?
Well, this is where classical mechanics gets a major rewrite. We're talking about variable mass systems. Suddenly, the standard force equation isn't just mass times acceleration anymore. You actually have to account for the rate of change of mass times the velocity. So whether you're looking at a raindrop accumulating water as it falls through the sky, or a massive rocket burning thousands of pounds of fuel every single second, this transfer of mass fundamentally alters the object's momentum in real time.
And honestly, the folded chain problem illustrates this perfectly. Imagine a flexible chain folded in half, dangling from a fixed point. If you let go of the free end, you'd naturally expect it to fall at standard gravity, right? But get this, a folded chain actually falls faster than free fall. Why? Because as it drops, individual links are transferring from the moving side to the stationary side. That transfer of mass from moving to stopped actually adds an effective downward force on the falling side. It sounds crazy, but the math and laboratory experiments absolutely prove it.
So, how does this quirky physics quirk build into the core mechanics of rocket propulsion? Let's dive into Section 2, the flat car analogy, momentum in steps.
Picture this. You've got a stationary flat car loaded with heavy blocks, or, say, people, who want to propel the cart forward by jumping off the back. Now, if they all jump off at the exact same moment, the cart gets one big, singular push. But if they jump sequentially, one after the other, the cart ends up reaching a higher final velocity. It all comes down to how momentum is conserved step by step. As the cart speeds up, the next person to jump is actually pushing off a platform that's already moving.
The takeaway here is absolutely crucial. Continuously throwing mass backward to go forward, which is exactly what a rocket does by expelling gas, is wildly more efficient than ejecting it all at once. In fact, continuous ejection can yield up to a 40% higher final velocity using the exact same amount of mass. That is a massive difference.
Now that we know why continuous mass ejection is basically the ultimate propulsion life hack, we need to look at the math. Section 3, the rocket equation, mathematical master key.
Think of the fundamental action like this. A rocket expels mass backwards at a constant exhaust velocity just to generate forward thrust. Because the vehicle's mass is constantly decreasing as it literally burns through its fuel, the rocket accelerates faster and faster. It's essentially pushing against its own high-speed exhaust gas.
And that dynamic brings us to the famous Tsiolkovsky Rocket Equation. This elegant little formula is the undisputed law of the land. It tells us that our speed limit, our delta V, or change in velocity, depends entirely on just two things. First, c, which is how fast we throw that gas out the back. And second, the logarithmic ratio of our fully fueled initial mass versus our empty final mass. It's a really harsh, unforgiving mathematical reality that every aerospace engineer has to live with.
But how do you actually measure how good an engine is at throwing that high-speed gas out the back? That brings us to Section 4, measuring engine efficiency, measuring thrust.
Inside a rocket motor chamber, you have absolute immense chaos that is being incredibly precisely controlled. You've got extreme pressure differences between the inside of the chamber and the outside atmosphere. Combine that with massive propellant ejection and you get a sum of forces. How well the engine's throat and that iconic bell-shaped exit nozzle manage and integrate these forces completely dictates our effective exhaust velocity.
In the currency of spaceflight, specific impulse, or ISP, is pretty much everything.
It tells engineers exactly how efficiently an engine translates its super heavy liquid or solid fuel into sustained thrust over time. Functionally speaking, specific impulse is perfectly equivalent to a rocket's effective exhaust velocity. A higher ISP? That means you can hit your target speed while burning way less propellant.
Unfortunately, the rigid math we just went over sets a nearly impossible physical barrier for actually getting to orbit. Welcome to Section 5, Tyranny of the Rocket, the Physical Barrier.
95%. Just let that sink in for a second. To achieve the immense orbital speed required for a single-stage-to-orbit vehicle, using current chemical rockets, roughly 95% of the rocket's entire liftoff mass has to be fuel. That leaves a measly 5% for the heavy metal engines, the structural tanks, the computers, and your actual payload. It leaves literally almost zero room for error, which is exactly why true single-stage-to-orbit vehicles just haven't been successfully built yet.
So we call that the tyranny of the rocket equation. But rocket engineers aren't ones to just give up. They've developed a brilliant and highly explosive workaround. Section 6, the multi-stage solution, beating the equation.
By simply splitting the rocket into separate stages and intentionally dropping the dead weight of empty tanks mid-flight, we completely rewrite the math. Think about it. A single stage has to drag massive, empty steel and carbon fiber structures all the way up to space. A multi-stage rocket discards that useless mass the second it's empty, meaning the remaining fuel can accelerate the suddenly much lighter payload so much faster.
The launch sequence itself is just a masterclass in physics optimization. The beefy lower stage fires in the thick atmosphere, where you desperately need massive thrust. Then, engineers sometimes use this incredibly aggressive technique called hot staging, where the upper engine literally fires before the empty lower stage even detaches. This keeps the momentum going perfectly and ensures the liquid propellant stay neatly settled at the bottom of their tanks. Once that dead weight separates, the upper stage just coasts highly efficiently in the vacuum of space.
But dropping dead weight isn't quite enough to win the game. We also have to constantly fight gravity losses. Rockets are physically punished if they ascend too slowly through the atmosphere. If a rocket hovers or climbs too sluggishly, it's basically just burning energy to fight Earth's downward pull without actually gaining the horizontal velocity it absolutely needs to achieve orbit. It's like paying a heavy gravity tax. So, to squeeze every last drop of efficiency out of the system, we use some literal planetary-scale life hacks. First, we launch as close to the equator as possible, facing east to steal the Earth's rotational speed. That gives the rocket a free boost of up to 466 meters per second. Second, we do something called a gravity turn. Instead of fighting with the engines to steer the rocket, we tilt it slightly and just let gravity naturally bend the trajectory into a horizontal orbit. It saves a ton of fuel and really reduces the massive structural stress on the vehicle.
Understanding these rigid rules of momentum is what lets us hack our way to the stars. From the mind-bending reality of a folded chain falling faster than gravity to outsmarting the tyranny of the rocket equation, these physics dictate absolutely every move we make in space. But it really leaves us wondering, right? As we demand heavier payloads and faster trips to Mars and beyond, what brilliant workaround are engineers going to dream up next? Are we looking at nuclear thermal rockets, ion drives, or something we haven't even conceived of yet? Keep learning, keep questioning, and I'll see you in the next explainer.